Thank you. So before I begin, I would just like to thank the organizers of Carry On. This is the first time for me, so they really did an excellent job of putting this all together, and also all the speakers who gave talks at Carry On. So I really feel I've learned many new things. I'm really happy to be here. So I'm Radu Popescu. I work at the CERN, where I develop software. And today I'm going to talk about the CernVM File System, which is the project I'm working on there. So, as you may know, the CERN, which stands for the European Organization for Particle Physics Research, is the lucky home of the Large Hadron Collider, which was involved recently in the discovery of the Higgs boson. This is the world's largest particle accelerator right now, so for the moment. And of course, on this image, you don't really see the text very clearly. The accelerator is outlined by the yellow circle. So just to give you a sense of scale, this is the accelerator, the tunnel, and here you see the city of Geneva. This. So you could put it inside the circle easily. And here you see the Lake Geneva, Lake Léman, and behind you see the Mont Blanc. So if we go inside the tunnel, we see that it's 27 kilometers circumference, and it's about 100 meters underground, and the accelerator is eating up around 180 megawatts of power. So again, for scale, all the combined households of Geneva are around 180. So it's really the biggest consumer of power. This is not very eco-friendly, maybe, I don't know, but this is it. So the beams, there are two beams running in opposite directions around the accelerator. Each one is around 7 tera electron volts of energy. So the energy of a particle is around that of a mosquito buzzing around, but the combined energy of all the particles in the stream is equivalent to that of a speeding train. So just as a fun fact. So at 4 points around the length of the accelerator, there are these so-called detectors. So there are 4 major experiments that are operating and maintaining these so-called detectors. These are very large devices. They're located in caverns. So let's say the height of a man is about this big, and the one for Atlas and CMS, so these are general purpose detectors that are able to do all sorts of physics experiments, and maybe they're a bit more well known because they were involved in the Higgs boson discovery. But the other two are also very interesting. For instance, Alice here, with its very characteristic magnet, they are the only ones accelerating very heavy ions, heavy metal ions, in an attempt to reproduce the conditions right after the Big Bang. Of course, like if you want really details about these things, I'm not the person to ask because I'm not a physicist, but there's a lot of resources available for this. Now, each one of these detectors has one of these devices inside. This is about this big, which is the actual silicon tracker, so the digital detector. This is very similar to what you have in a digital camera, but of course the performance is quite different. Now, if this image is familiar, it's because it was used in 2013 by the thrash metal band Megadeth for their cover of their album Super Collider, which I haven't listened to yet, but I thought it was interesting trivia. So, Mustang et al. Now, back to the silicon tracker. So, in principle, it's similar to a digital camera sensor, but you have 100 million channels in each detector, and it should be able to react to a bunch crossing, so to an event, every 25 nanoseconds. And the idea is not just the ability to record these things. These detectors are backed by very complicated hardware, which is supposed to reduce the size of the data going into the hardware, because trying to store the raw data coming out of the detectors is impossible. So right now we're seeing something along the lines of 1 petabytes per second internal data rate, And the experiments are storing around 5 petabytes of data per year. So you see the amount of reduction happening. So this is including the derived data sets. And by the end of 2025, which is the latest planned experiment that the CERN is planning, we estimate around 100 petabytes of data, so a 20-fold increase. Now, regarding the size of the code used by each one of the experiments, we're talking about 5 million lines of code. Okay, this is not negligible, but I've heard that it's tiny. It may be tiny by enterprise standards, but this is what there is there. Now, an important thing about the CERN is that while the site in Geneva is the house of this accelerator and the detector equipment, is not just there. Basically, the CERN is a worldwide collaboration spanning 42 countries and around 170 centers. So you have physicists all around the world which are taking part in this science, and that's why the CERN is operating the so-called worldwide LHC computing grid. So you have computers from all these sites which are pooling their resources and giving this interface of this view of a worldwide grid. So when you're a physicist and you're doing simulations or analysis, you're submitting jobs to this grid, hoping that they work like Dave said, and you don't know actually where they go. They could go to another continent and this is actually this visualization is the WLCG live map, which is available through Google Earth. And this is a snapshot that I took last week. So you see at that particular moment, there are around 300,000 running jobs in the grid, and using around 460,000 CPU cores. And all this amounted to 17,000 gigabytes per second transferred through the grid. So it's not negligible. Now, about the software stacks. So each experiment maintains its own software to do the specific physics of their collaboration. And on each collaboration, you have hundreds of developers ranging from novice, more physicists who do a bit of coding to very experienced programmers. And I think right now, if you look through these repositories, you have something like 10 to the power 8 binaries which have accrued. And the experiments are outputting around 1 terabyte a day of nightly builds. Everything is rebuilt every night, and actually the physicists really like using cutting-edge tools. So basically the continuous integration and nightly builds of their experiments involve or start with compiling the compiler. Usually it's the latest stable version of GCC, and you bootstrap from there. So there's a lot of stuff coming out of the continuous integration, and all this goes to around 100,000 machines worldwide. And of course, like nightly builds get pruned after this point. Not everything has to be archived, but still the daily production releases are stored. Also due to these attempts of doing reproducible research, and so it's important that they are kept around. Now, in these conditions, there was the origin of this CernVM file system. So in around 2008 or 2009, there was the idea of creating the so-called CernVM, a very configurable appliance to be used on the grid and on laptops of physicists, and basically giving them access to the entire software stack of the CERN wherever they go. And this was very impractical due to the large size of these VM appliances. They were like a few gigabytes of size. You had to remake it every day. If you had different configurations, you have let's say 1 gigabyte for each configuration. So the idea was to solve this problem. So the problem of serving these software stacks. We're not talking about the data. We're talking about the executables. So the idea is to serve these things through a file system and user space interface. So this was the birth of CERN-VM-FS around 10 years ago. So it's implemented as a Fuse module. I think I don't know if you're familiar with the Fuse interface of Linux. And it makes available the content of these software repositories, which are around 1 to 10 terabytes of size. So not really huge by, let's say, big data standards, but they're around 10 terabytes of size, full of very small files. And these are made available lazily, so on demand, through a global HTTP cache, all the way down to the individual clients. And each one of these repositories is mounted into the /CVM-FS file system namespace. And of course, important thing is like these are read-only views. So this is a content distribution system. They're not made to all make changes to the repositories and synchronize. Also important is the fact that HTTP is used as a transport everywhere. So you have good chance of being able to pass through the firewall and through the different corporate systems, or I don't know, enterprise networks, or what have you. This is very simple and reliable. Now, the main components, as I said, are a fuse module. So this is a single process running in user space, which is talking to the fuse kernel component. And this can be complemented with different cache plugins. So these make the performance, this increase the performance in different use cases. For instance, you can imagine that on a supercomputer or on a cluster where you have very fast network in between the nodes of the cluster, but relatively slow connection to the exterior, you would like to exploit this, and it's possible to exploit it through a specialized cache plugin. So data is brought into the cluster once, and then it is distributed as needed to all the workers. Then you have the server tools, which are implemented as stateless command line tools. So on the single writer machine that is assigned to a specific repository, you will run these command line tools and publish new changes to the repository. And then for the distribution, so for everything from the repository to the client, we are able to use standard HTTP tools. So you are able to use Apache, Nginx, and things like Squid proxies. You don't need to write special code for this, and you can rely on existing very stable solutions. Here I mentioned the Stratum 0 and Stratum 1. So the Stratum 0 is the authoritative copy of each one of these repos, and clients will not connect to it directly. They will connect to the Strata 1. So these are full replicas of these repositories, and they are globally distributed. Now, a few important data points regarding the design of the file system. So for storing data, the core idea is immutable blobs which are content addressed. So here I put a star to remember that since we are at a programming language conference, these are concepts that are seen in, for instance, in functional programming languages, where you have things like referential transparency. You know that the name will always refer to the same data, and it will never change. So these are the principles that we have also used in CernVM-FS. And for instance, things like deduplication in this context come for free, because if you end up with the same data, you already have it. And we also do compression for this. And then for the metadata, you have the so-called catalogs, where the state of the entire repository at a given point in time is encoded in a Merkle tree. So the idea is that we iteratively hash the contents of the repositories, and we build up a tree of hashes where the root hash, if any change in the repository occurs, this will be reflected all the way up to the root hash of the tree. This is similar to Git in principle, in implementation. And this root hash that comes out of the Merkle tree is put in a repository manifest, which is, imagine it as a text file, which gives you the entry point into the repository. So this is the first thing that the client downloads when he wants to access the repository. This is put in the manifest, and the manifest is digitally signed. So there is this verification steps. You know that the client has a guarantee that what he will receive from the servers is what he asked for. So this is very useful. And then, because of these design revolving around immutable content addressed storage, it's also easy to implement things like versioning and snapshots, and we have features for this. Now, the last point is definitely not the least important. The fact that everything is pole-based. So all the connections and interactions between the client and the servers is initiated from the client. These are HTTP connections coming from the client, so this means that we'll never run into trouble with firewalls. This system works as reliably on a grid site, at the grid site, on a cluster, as, let's say, in a hotel on spotty Wi-Fi connection. So there will not be any problem in connection. Of course, difference in speed, but this is another thing. Now, the fact that we are passing through a layer of caches to the stratum 1, this gives a lot of resilience to the reading operation, and it also makes it very scalable. And if any cache node, let's say, goes down or becomes unreachable, the client has logic implemented to route around this and to find another suitable candidate in order to reestablish the connection all the way to the stratum 1 server. And also because of all these caches, which there exist caches also on the client, if the connection is severed, the client is still able to continue based on the contents of his hot cache. It just doesn't receive any changes anymore. So as I mentioned earlier, the clients are always talking to the stratum 1 servers, never to the stratum 0. The stratum 0 is where the writing takes place. And just to give you an impression, this is the current network of stratum 1 servers all around the world. So in the UK, in the Netherlands, in Germany, in Asia, and in the US. All of them are serving their clients, their closest clients. So having covered reading, let's talk about publication, about writing into these repositories. So I mentioned that the system is designed around a single writer. So you have a centralized machine which is close to the repository storage, which is doing the writing operations with the help of these stateless command line utilities that I mentioned. And once we're entering some sort of transaction phase, we are constructing a read-write view of the repository for the sake of this transaction using union mounts such as overlay-FS or AUFS. And at this point, files are compressed and hashed, and they are written to the repository storage. So on the writer machine, the repository storage is either accessed through NFS or through, for instance, an S3 API. And we are able to use any backend for this storage as long as this backend is able to export its contents through standard HTTP. So that's why S3 is very useful for this. And after the files are compressed and hashed and written, the new metadata catalogs are created and published. And finally, after all of this is done, all the data is present in the repositories, we are able to switch the manifest of the repository with the new one, and this in a single atomic step, the new state of the repository becomes available. So this is important because at no point the clients will see the repository in an intermediate state. They either see the old version or the new one, not anything in between. So to give you an idea of the actual workflow, so on the centralized release manager machine, you connect to it through SSH, and then you run CVM-FS server transaction to initialize the transaction. You can also specify a specific repository if you have multiple repositories installed on the machine. And then you start editing the files that you want, and finally you publish. And at this point, all the heavy work is done of hashing, compressing, and writing. So this sort of approach has pros and cons. Pros, it's very straightforward to use because you just log on and you run some set of commands, and it also hides somewhat the distributed nature of the system. So you may not be aware that actually you're talking to a different machine. What was the saying that the distributed system is when a machine you didn't know existed is crashing and makes your work impossible. So And of course, this is good for scripting too. The fact that you have command line tools, this is 99.9% of the updates happening to these repositories are in an automated setting in a continuous integration system. So the cons is there's not really support for concurrent writing. You have two people logged in or two users logged into the same machine, it will run into trouble. And the thing is, like, we actually have performance issues for very large change sets. We have clients which are reporting this. So right now with these tools, you are able to make use of all the cores on a single machine. It's parallelized. There's no wasted resource there, but you're not able to scale out. And they are trying to publish an amount of files where they're reaching the limitation of this, and they would like more. So we set out to improve this. And of course, like, the moment you have users logging into a machine, well, this is unsafe and should be improved in some way. Now, before setting out to do anything, it's important to note the properties and the constraints of the system we are working in. So we are talking about the file system and a file repository. So in our case, consistency is key. So nothing we should do with this repository should leave it in an inconsistent state. This is something we cannot afford. And given the large number of clients that you can potentially see, we also would like the highest availability possible, but always given 0.1, so highest availability possible as long as consistency is maintained. But the design of our software gives us some potential avenues to explore when it comes to concurrency. So we have the immutability of our data and the fact that it's addressed by its content. And this means that you will not have two entities trying to write to the same file at the same time. And then you also have the fact that copying these objects into the repository storage is idempotent. So if it happens multiple times, it should not change anything. And of course, the data we are working with is a directory tree. So this gives you clear branches where you can operate in parallel without stepping on the toes of a neighbor, let's say. And of course, this is not embarrassingly parallel. You have a critical section in your algorithm which involves updating the metadata catalogs. So updating the Merkle tree that represents your repository, and at the end swapping the manifest. But luckily, this is not a computationally heavy job that takes a long time. So this is a short critical section at the end of the heavy work. So this summarizes the existing architecture what I've been describing. You have a user. From his machine, he goes to the release manager over SSH. And there we have the Fuse module and the server tools. And this machine sees the central storage of the repository over NFS or S3, and it publishes its contents to the Stratum 1 servers over HTTP. And how we improve this is by doing this. So now we see that the central release manager machine, we cut it in two, into the user-facing part and, let's say, the storage gateway. And now each user is able to operate its own release manager machine, which can be generated on demand. There's much less state there, and he does the heavy work of processing the changes to the repositories there, and then finally this release manager is publishing these changes to the storage gateway, but it's talking through a well-defined service API that is defined now, and afterwards is the same thing. Of course, in this approach, we can also run multiple storage gateways with a replica of the session data to increase the availability of the system. And in our improved workflow, we see that the steps are the same, but now we have two users each on his own release manager machine. They're acquiring transactions, and they're starting transactions and acquiring releases on separate subpaths of the repositories, and finally they're able to push there without any problems. Now, in this new approach, the CernVM-FS release manager machine, so this one is the consumer of our new storage gateway API, and his job is to try to acquire a lease from the storage gateway to the lease being given on a specific subdirectory of the repositories. If he acquires the lease, he's then free to hash and compress and send the files over. And of course, this is an important thing now. It's a separate machine to the gateway. And okay, this is maybe a logistical matter, but we're giving more freedom to the user of managing this resource and deploying based on the size of their load. And then the second part is the storage gateway, which basically serves as a distributed lock manager for all the release managers. And its job is to check the rights of clients, whether they have these rights to modify the repositories it's managing, and then hand out leases to different repository subpaths. And of course, in the case of let's say like a high availability deployment, you have multiple replicas of the session data. And I guess in the CAP theorem classification, this would be a CP system. So we are okay with losing availability to our system if some sort of network trouble happens. We wait for a restart, all to maintain the consistency of the repository. And of course, the storage gateway is the one that receives the payloads from the release manager clients and is writing them to the authoritative storage. Now, for the implementation of this new component for the storage gateway, we actually went with Erlang OTP. I didn't mention it, but all the other code is C++. So it's C++ is actually the main language in use at the CERN, from systems all the way to the physicists who are doing their analysis in C++ too. So this is one thing to keep in mind. Now, we chose Erlang and OTP because it seemed very suitable for this sort of concurrent and distributed applications. And you can think of this also as a sort of pilot program for us. So if we see that for this use case it's working well, we may deploy it into other sections too. So I don't know if you're familiar with Erlang and OTP. The language is built around the concept of around the model of actors. Actors are basically lightweight processes managed by the Erlang VM, and they have complete memory isolation. So the only way two actors can interact is by sending messages to each other. So there's no shared memory made available to them. The language has full immutability of values, which in certain cases makes things very clear. And core aspect, I think if you were at the keynote this morning, the keynote of José Valim, he did me the favor of explaining already these things. So a supervision tree is if you have a tree of these actors, these processes, which implement the logic of your application, you will only focus there on the happy case. So error handling, you will not implement it there. You will let these processes crash because it's very cheap to also restart them. And you will implement a parallel tree whose sole purpose is implementing recovery and error handling logic. So this errors start at the bottom of the tree, and basically the lowest level supervisor says, there was an error with the guy I'm supervising. What should I do? If it knows how to do it, it will just restart it. If it says that, I don't understand this error, it's above my pay grade, then he will say, I'm dying too, and let the error propagate up to his own supervisor. And in practice, this gives you very resilient systems. And it's also quite simple to work with this. So we felt that there wasn't a lot of risk by trying this new technology, due to the fact that the language and the framework and the virtual machine are battle tested at this point. So they've been in use for more than 30 years at Ericsson for running systems which are much more critical, let's say. And of course, last but not least, the system gives you many ways to interact with C++ code. So since most of our code base is C++, this is really important to us because we cannot afford to not reuse it. So the architecture of this application is very simple. And with the exception of the HTTP front end, which we implemented with the Cowboy Erlang server. So this is the standard, let's say, standard Erlang server that is used by Erlang developers right now. I think also the Phoenix framework mentioned by Jose Valim is also using this Erlang server. So they don't implement their own Elixir server; they're using this one. But with the exception of that, everything is implemented with the base distribution of Erlang. So with the included batteries of the distribution, we implement the main business logic using OTP generic servers. So the generic behaviors are let's say a way to implement some sort of behavior polymorphism in Erlang. And we're using Amnesia, which is the built-in database or key value store for the persistence of session data, and then the computationally heavy parts are implemented in a C++ program, which is coupled to the main Erlang application through a so-called port driver. So think of it as a co-process. So you have pipes going in and out of the process, and you have a request-reply cycle happening. So the same thing, you have on top you have the HTTP Cowboy front end. It's receiving requests from the release managers, and it's sending them to the backend. And the backend is the one who dispatches them to the relevant module. So all these things are basically concurrent processes in our applications. You have auth handling the access control list, and then the lease module, which is checking the availability of leases for different subpaths. And finally, once it's time to receive payloads, these go to the receiver, which passes them, which forwards them to the C++ workers, which are usually meant to be run 1 per core or something like this. And okay, it's also important to note what sort of experience this was for us. So we're coming from C++. So the fact that you have OTP, the framework for building application, comes with a lot of stuff. Let's say so you have so many tools that you can use there to build your application. And the fact that you can do live tracing and inspection, again, it was shown in the morning keynote that you can connect an observer to a running node and see exactly what's happening with the message queue, all the processes, and this is really great, and we're not used to it. The fact that you have immutability and functional programming concepts, again, this can simplify certain algorithms, and certain parts can be made very clear. And of course, the entire language, since it's focused on concurrency, it really feels like a domain-specific language for writing concurrent code. You do this effortlessly, and it comes with things like unit testing and integration testing frameworks, quick check by John Hughes, and dialyzer. Dialyzer means you can annotate your functions. So I forgot to mention that. So the Erlang is dynamic language. You can annotate it with type information, annotate all your functions, and then this is a checker. It's I think it's using success typing to see if what you have there is actually achievable. And we have good integration with C++. Now, of course, given our C++ experience, which is not the most, let's say, the strictest type system, but still, it's a bit more strict than the dynamic typing experience of Erlang. This was a bit weird, but I have to say that due to the immutability of the data, in practice it's very manageable, even though you have dynamic typing. If this is not your thing, you are helped by the immutability. And there are some things which it's more of a lack of polish, such like the default errors are very verbose, and it takes a while to get used to it. And some parts of the API are not really well documented. So in summary, we were able to get more concurrency and handle a lot of like some more traffic for our clients, and also give them more flexible configuration for their needs. Now, to end, I would just like to mention a few other projects and activities related to CernVM-FS. there's a technical student in our team which is now working on a Docker plugin. So if you've ever used Docker and you have to download an image that contains something like 10 layers, and you have to wait on a slow network for all the layers to completely download before actually running your 5-second operation or what it may be, the thing is, like, this will come in handy. It's a plugin, you install it, and then it makes available the contents of these images from CernVM-FS repository. So let's say downloading the layer at the beginning is instant, and then the files are fetched on demand as you are using them. So in the case of an image where you have 1 GB image size and you're using 2 files, this will give you a big speed up. So he's working on this, and you can take a look at this code at that link. We also are trying to improve the experience of CVM-FS on HPC machines, which have special configurations, reduce connectivity from the nodes to the outside. And we actually managed to work with the guys at CSCS in Switzerland, in Lugano, which is the Swiss supercomputing center, to get it running on their machine Case Dent, which is the number 3 of the top 500. And there's going to be a talk by my colleague Jakob Blomer in Frankfurt 2 days from now, so maybe it will be made available online. And next year we are celebrating 10 years of this project, and there's going to be the CernVM-FS workshop at the CERN, so at the end of January. If you are interested and would like to join us, you are more than welcome. So this is the team working on this. So there's me, there's Jakob Blomer, my colleague, and his PhD thesis was the origin of, was the start of the CernVM-FS project. So he knows it best. And Gerardo Ganis, our team leader. Peter Hiraut, a former technical student who was working more on the CernVM appliance. And Nicola Hadi, the current technical student working on the Docker integration. So thank you very much, and if you have questions.
You mentioned a number of times the compression, hashing, and transmission phases and all these things, and also the fact that there's the duplication. So could you speak a little bit more about the precise order in which hashing, compression, deduplication happens? Because I imagine that with large data volumes it makes a big difference.
This is a good question, but I wouldn't really know how to answer it precisely right now. I would have to check, because obviously this can have a great impact.
Do you worry about conflicts with your hashing?
Well, I think right now the default hash is SHA-1, but I think for this use case we're still safe, because the recent exploit wasn't a pre-image attack. But we have full support for switching the hash. It's just that most of the repositories right now are using SHA-1, but you can switch this, and you can even have a single repository. Half of the objects are SHA-1, half of them are in another hash. So we can change as we need.
But if you have multiple hash, can't you have the same content twice?
The idea is that you have, yeah, you could have it once in one hash and one in the other. I think there's something to do that takes care of this, but I think having half and half probably isn't the easiest way to go for. It's probably you try to avoid it, but.
Questions? Okay, so let's thank Radu again.
Thank you. Accelerator right now, so for the moment, and of course, like, on this image you don't really see the text very clearly. The accelerator is outlined by the yellow circle. So just to give you a sense of scale, this is the accelerator, the tunnel, and here you see the city of Geneva. This. So you could put it inside the circle easily. And here you see the Lake Geneva, Lake Léman. And behind you see the Mont Blanc. So if we go inside the tunnel, we see that it's 27 kilometers circumference, and it's about 100 meters underground. And the accelerator is eating up around 180 megawatts of power. So again, for scale, all the combined households of Geneva. Thank you. So before I begin, I would just like to thank the organizers of Curry On. This is the first time for me, so they really did an excellent job of putting this all together, and also all the speakers who gave talks at Curry On. So I really feel I've learned many new things. I'm really happy to be here. So I'm Radu Popescu. I work at the CERN, where I develop software. And today I'm going to talk about the CernVM File System, which is the project I'm working on there. So, as you may know, the CERN, which stands for the European Organization for Particle Physics Research, is the lucky home of the Large Hadron Collider, which was involved recently in the discovery of the Higgs boson. This is the world's largest particle. Of course, like if you want really details about these things, I'm not the person to ask because I'm not a physicist, but there's a lot of resources available for this. Now, each one of these detectors has one of these devices inside. This is about this big, which is the actual silicon tracker, so the digital detector. This is very similar to what you have in a digital camera, but of course the performance is quite different. Now, if this image is familiar, it's because it was used in 2013 by the thrash metal band Megadeth for their cover of their album Super Collider, which I haven't listened to yet, but I thought it was interesting trivia. So, Mustang et al. Now, back to the silicon tracker. So, in principle, it's similar to a digital are around 180. So it's really the biggest consumer of power. This is not very eco-friendly, maybe, I don't know, but this is it. So the beams, there are two beams running in opposite directions around the accelerator. Each one is around 7 tera electron volts of energy. So the energy of a particle is around that of a mosquito buzzing around, but the combined energy of all the particles in the stream is equivalent to that of a speeding train. So just as a fun fact. So at 4 points around the length of the accelerator, there are these so-called detectors. So there are 4 major experiments that are operating and maintaining these so-called detectors. These are very large devices. They're located in caverns. So let's say the height of a man is about this big, and the one for Atlas and CMS, so these are general purpose detectors that are able to do all sorts of physics experiments, and maybe they're a bit more well known because they were involved in the Higgs boson discovery. But the other two are also very interesting. For instance, Alice here, with its very characteristic magnet, they are the only ones accelerating very heavy ions, heavy metal ions, in an attempt to reproduce the conditions right after the Big Bang.